In 1916, this single scientific paper landed like a thunderclap. It completely rewrote our idea of the universe, changing it from just a static stage where things happen to a dynamic actor in the cosmic drama itself. So let's dive into the document that really is the foundation of modern physics, Albert Einstein's General Theory of Relativity.
You know, the whole thing kicks off with a question that's so simple, but so ridiculously profound, it threatened to topple 2 whole centuries of physics. He just asked, what if gravity isn't a force at all?
Now, to really get why this was such a huge deal, we have to see the problem he was wrestling with. There was this deep, troubling crack in Isaac Newton's perfect universe.
And what's so wild is that Einstein was actually critiquing his own work. His 1905 special theory of relativity was a massive success, but he knew deep down it wasn't the full picture. He even says so right here in the paper. He saw an inherent epistemological defect, which is just a fancy way of saying there was a major logical flaw. And the big missing piece? Yeah, it was gravity.
This basically set up a clash of the titans. On one side, you've got Newton's gravity, this mysterious force that just acts instantly across any distance. And look, it worked great for things like falling apples and orbiting planets, but on the other side, you've got Einstein's own special relativity, which set a hard and fast speed limit for the entire universe, the speed of light. Nothing, not even the pull of gravity, could go faster. These 2 ideas just could not coexist.
So how on earth do you solve a problem that big? Well, for Einstein, it came in a flash of insight that he later called his happiest thought. And trust me, it changed everything.
Okay, so picture this. You're in a windowless elevator, way out in deep space, totally weightless. Suddenly, the elevator starts accelerating upwards. You'd feel yourself getting pressed into the floor, right? So here's the question. Is there any experiment you could possibly do inside that box to tell the difference between that feeling of acceleration and the feeling of just standing still on Earth?
In the punchline, the big realization for Einstein is that you can't. You absolutely cannot tell the difference. The effects are identical. He points out this remarkable property of gravity. It gives the exact same acceleration to everything, no matter what it's made of. A feather and a cannonball fall at the same rate. This simple, everyday observation was the key that unlocked the whole thing.
And this is the core of his new theory, the principle of equivalence. Put simply, it just means gravity and acceleration are 2 sides of the very same coin. They are fundamentally indistinguishable. And with that, bam! Gravity is no longer some mysterious force reaching across space. It's a property of space-time itself.
Okay, so the idea is brilliant, for sure. But an idea is one thing. You have to be able to describe it, to write it down, and Einstein was now facing this monumental challenge. He had to find a whole new mathematical language to describe this new curved reality.
I mean, really think about that for a second. If massive objects are literally warping the fabric of space and time around them, and that warping is what we feel is gravity, what does that even look like in an equation? The normal geometry you learned in high school?
Yeah, that's not going to cut it. He had to go on this deep dive into a type of math that, back then, was super obscure and incredibly difficult. Now don't worry, we're not about to do tensor calculus here, but it's worth seeing just how complex this stuff is. He had to master this whole new language because it's the tool for doing geometry on curved, warped surfaces, exactly what he needed.
This took him years. We're talking years of just grinding it out, working with mathematicians to build this whole framework from the ground up. Every single symbol you see on a page like this, it's a piece of the puzzle, another step toward this radical new vision of the cosmos.
And there it is. This was the language he needed. Armed with the power of tensors, Einstein was finally ready to write the new laws of the universe.
And that brings us to the grand finale of his decade-long quest, the law of gravity, completely and utterly rewritten.
And here they are, the Einstein field equations. I know it might just look like a string of symbols, but what you are looking at is genuinely one of the most important equations in all of science. This right here is general relativity.
So what does it all mean? Well, thankfully, it's been boiled down to this absolutely beautiful poetic idea from the physicist John Archibald Wheeler. Matter tells spacetime how to curve, and spacetime tells matter how to move. That's the huge shift. Space isn't just an empty, passive box anymore. It's this active, flexible fabric, and it's being shaped by everything inside of it. But look, a beautiful theory is great and all, but in science, that's not enough. You have to be able to test it. And Einstein's theory made some seriously bold, specific predictions that could actually be checked against reality. It was time to look for proof in the stars.
And the first big test was this nagging little mystery right here in our own solar system. For decades, astronomers had noticed that Mercury's orbit, it wasn't quite right. It wobbled a little bit every time it went around the sun, in a way that Newton's laws just couldn't explain.
Now, the discrepancy was tiny. Almost nothing. A shift of just 43 arcseconds per century. But it was real, and 100 years of observations confirmed it. So if general relativity was the real deal, it had to predict that exact number. No wiggle room.
And you know what? It nailed it perfectly. In Einstein's own words from the paper, his calculation gives a rotation of 43 arcseconds per century, corresponding exactly to astronomical observation. This was a massive win. He later said that when he saw the numbers match up, he felt heart palpitations. He knew he'd found something deeply true about how the universe works.
And that was just the beginning. The theory just kept on winning. It predicted that massive objects should literally bend the path of light, which was proven during a solar eclipse in 1919. It predicted that time itself runs slower when gravity is stronger, something your phone's GPS has to account for every single second just to work correctly. It even gave us the tools to understand that the entire universe is expanding.
When you really think about it, Einstein's journey teaches us that even our most basic, fundamental ideas about the universe can be completely upended by one brilliant question. For centuries, gravity was a force. Now, it's the geometry of a curved reality. So that kind of leaves you with one final thought. What other truths that we take for granted are just waiting to be rewritten?